we are going to see some examples on this one, the LSTM, and then we are going to move to the LSTM code. Okay, so one example that I was unable to complete within the time. Let us just go through that one. Just confirm it if this is visible or not. The screen is visible or not.
Yes, sir. Visible, sir.
Okay, sir. Thank you. So let us just go through what we have covered till now. So we are discussing about this LSTM in this way, and we have talked about uh, basically various gates and what are the selective read, write, and forget is all about. Okay, so these were the weights that we have talked about. So along with that, we have also forget that here also one weight was there, so you may accordingly assign the weights. Okay, so it is similar to that of the recurrent neural network, but some weights have been basically introduced. Okay, so I think these concepts, so basically LSTM can be implemented in various ways. Okay, so this one is one way. Another way, you can make some changes here, how you are going to basically incorporate uh, the current state information to the long term memory. So you can basically customize this architecture according to your requirement, and based on different changes that have been made, there are various basically methods that has been evolved over the time. Okay, so uh, let me just go through one another approach before going with the next concept. So let me just okay. So basically, I will request all of you to remember this concept. Okay, whatever we have seen here, just remember few things, uh, that within state, this cell state, input, and the output, this value, this one, the we can say that uh, transient uh, long-term memory, or the potential long-term memory candidate value. Okay, so just come to this intuition. Let us just recall what we have talked about. So let us just make it as h. Okay, instead of s, I am writing it as ht minus 1. So what this ht minus 1 was, this was the short term memory. Okay, this was the input, and this is the next short term memory. So let it be h. Okay, now the thing is, we are having we have some input, and that input is nothing but a vector coming from a previous state. So this is what we can say. So here it is. Okay, just suppose we are talking about some next RNN unit. So this is what we are going to take as input from the previous state. Okay, so now, so this is the previous state information that we have. This is the current input vector, the embedded vector we can say. So if we have the word, sorry, if we have word, then we can either go with the one hot encoding, uh, either we can go with the one hot encoding or embedding technique. Okay, and then we can operate using this LSTM or RNN model. Now the thing is, the three operation that we need is read, write, and forget. And if I ask you what was the purpose of this read, write, forget, I think you all of you can recall that one. Okay, it was basically, the purpose of this one was to control how we are going to basically carry forward the information, and how we are going to use the past history for the current state. Okay, now so let us go through this one and try to map these intuition one by one. So basically we are having this weight vector, this u, and this is the next one. So we can make it o or whatever you want. Okay, even from there we can also make some output vector. Let it be sigma only. Okay, we are talking in terms of sigmoid activation function. So some output may also be there. This is the next state. So what we want is, in selective write, what was the purpose? What we were doing? What is the purpose of selective write? Anyone, please? Hmm? From history, and how does it affect? How will it affect the long-term memory? So basically, we knew that if we talk about the write, okay, so write was in some way, it was attained using that input gate, and the purpose of the input gate was to how much information from the current state computation be contributed to the long-term memory. Okay, but the interpretation is just the how much amount we are going to add. So yes, you are right in some, to some extent. Yes, yes, exactly. So then this multiplication, we all know what it will do. Suppose in simple case, if we say that some of the output we are going to ignore from this previous state, so it can be made, it can be made possible just by making some of the entries zeros and other entries as ones. Means we can have, sorry, we can have the entries for this one as 0 0 1 0, something like this. Means wherever we want to take the input as it is, we can make it 1. Wherever we want to ignore the value from the previous state, we can make it 0. But this is the a kind of binary decision. Means either we are taking the whole history information, or we are ignoring, or we are completely ignoring some of them. Okay, but we are not going to be very crisp in that way. So definitely this sigma will be some fractional value, and that way it is going to have some value for each of the entries. Okay, that is a kind of weighted uh, information is being carried forward. Okay, so basically this is what I have talked now. So if you can recall, this is the h t minus 1, and suppose this is some output. Okay, and this output is nothing but, we say, a kind of a way, we can say, not forget, since we are talking about the write, a selective write, so it will be a kind of input gate. Okay, so if we apply this input gate, okay, somewhere by applying, if you can recall the previous part, it was the tan function that excused the info in range of -1 to 1. Okay, now so basically this, we are suppose this is a kind of output, and that output, if I can just go back to the slide, just explanation, this is we are talking about some output. Okay, this is one output, these are the some of the outputs here. Okay, so we are talking these about these outputs, and these outputs were implemented using the input gate, the FOR gate, or the output gate. Okay, so this CT minus 1 is what this is. So basically this input gate will have some x t minus 1, and then this h t minus 1, and if it will be applied on this one, it will produce the some CT intermediate value. Just look at here, this was the part, the intermediate value. Okay, so uh, the basic purpose is to just select the limited amount of value from here. Okay, and that will get propagated to the next level. So if we want to parameterize this one, so earlier we have seen this one. So if I talk about this one, what it is, so just come from this one and just look at what we are doing here. So we are applying some sigmoid function. So basically we are applying some activation function on what, on the, so just on this one, whatever output we are getting, then we are applying some summation function is there, and before that we have some multiplication. Okay, so the one input, the other input, so this is the xt minus 1 multiplied with the u naught. Okay, the output gate, and this one is the ct minus 2, which is basically the history, the short term, sorry, no short term, it is the long term information that is coming from the past. Okay, and plus if some biases are there. Okay, so if you can go with this one, so okay, so here if I ask you to write the function, what function this will be, the ct, can you write this function ct here? What will be the value of the ct? Can you write the value of ct? Yes. So this ct was nothing but this tan h, or suppose some weight was there, whatever weight is there, suppose I'm taking the star, and that was multiplied by some ht into ht and your input, suppose. Okay, and if you have some bias that was there, and the final ct was nothing but the output of this one multiplied by some value. So this would have been written like ct minus 1 plus it into this one. So just recall from this one where it is, this one, from this part, how this ct will be computed and how this ct will compute, will contribute to this value ct. Okay, this is what I have written. So you may basically go through this expression, you can compute it easily how they will look like. Okay, so but the, even though analogy is same, we are selectively reading, writing and forgetting, but if you will try to compare both of the approach that we have seen. There is a slight difference here. Okay, the way we are treating the selective read write forget here is slightly different from this, different than what we have talked earlier. So this is just a different way to basically interpret the LSTM model. Okay, and for more detail, you might basically, if you want to explore this one, you might also go for one NPTEL lecture by Mitesh Khapra. He has very well explained this concept. So it is another variant of LSTM that you can go with, and how you basically will be implementing the LSTM. Okay, so basically this is how the then selective read is being made. The selective read, the goal of the selective read is to produce this HT, isn't it? This is HT minus 1. This is CT. Okay. So this is the CT, and if you will compare this read operation, okay, so this input gate you can accordingly formulate. We have the input gate. Okay, we have the input gate. You can take this input gate in the expression here, or you can formulate it accordingly. Okay, you can just think of how we can parameterize this part, because see what we are doing, we are trying to control the information flow by using some gates. So these are the gates. Now we cannot use any random value as a gate. We need to learn the values of the gate, and that's why we need to parameterize these gates. Okay, now how you will parameterize this one, that the way you are parameterizing the these gates will basically make the different LSTM variants. Okay, so the way you are going to basically parameterize this input gate, output gate, and forget gate will deduce different variants of LSTM. Okay, so but the overall, the baseline of the LSTM is we must have some provision of selective write, read, and forget. Okay, so in the write, what we have done, we have contributed the information. Okay, we have contributed to the information that was coming as in terms of long-term memory. The purpose of selective read was to produce the information in terms of what will be fed into the next recurrent neural network unit. And if we talk about the forget, the purpose of the forget gate was to how much basically information from long-term information will be basically carried to the short term. So basically this how much information will basically be coming to the out sorry, how much information the forget gate, the intention of the forget gate was to control how much information from the long-term memory will be considered for the current state. Okay, so this way you can basically go through these concepts, and this is overall summary of how we can visualize selective read, write, and forget in a different way. Okay, so the baseline of this is the LSTM having different variants, and that variance depends on how information flow is controlled, or the gate mechanism is basically is applied. Okay, so this is one view of what the LSTM can look like. So I will share this PPT. You can just take an analogy of what we have learned here, and you can just see the small differences between the way we have interpreted here and the way that particular mechanism works. Okay, but still the motive is attained in both the mechanism. Okay, the standard motive is to control the information. Whichever way you like, you can implement the gating mechanism. Okay, the next thing is, okay, so the next thing was just this BiLSTM. Let me just quickly go through this BiLSTM. So the purpose of BiLSTM is, suppose some word we want to predict. Okay, it is having some initial sequence and initial tokens and the future tokens, and we want to predict this value. Okay, or some of the word depends on the past or the future words also. Okay, so in that case we go with if we want to, these two are available and we want to predict this value, or we want to learn this the context of this value. So for that case we go with the BiLSTM. Okay, and the architecture of this BiLSTM is something like, if I hope you remember the LSTM architecture, it is same as that one. Okay, this is basically in the reverse direction. If you can recall, we earlier we had just one way LSTM. Okay, we had the input from previous states. Okay, now this input will also be fed to this one. Okay, okay, uh, and we will have some output. Okay, now the output will be basically merged. Okay, basically this one is forward LSTM, and Okay, so this is how it works. So one unit, one unfolding will be in forward direction, and the other will start from the last. Means in if we talk in this context, the other will be starting at the end and will back propagate till the first time step. Okay, so this is a simple bi-LSTM architecture. It is just the stacking of two layers. Okay, the layer 1, layer 2. Okay, now so basically the next thing is that we are going to talk about the GRU. Okay, so I hope till this it is clear to all of us. uh, any question, can you repeat the NPTEL? So basically it is from uh, we need, I'm writing it, sorry, NB IIT Hyderabad. Okay, okay, you can refer to Vinny sir, sir's lecture from IIT Hyderabad. Okay, or for this one you may refer the other variant that I was talking through the example was basically explained by Mitesh Khapra. Okay, okay, so you can just go and explore these variants. Okay, each time you will refer to some material, definitely you will find some different variants. Okay, so the basis is what you want to basically, how you want to apply the gated mechanism. Is it that the standard one that you are going to use, or you are going to yes, so if you have done that course, definitely you would have gone through this example in the this LSTM. Okay, so anyway, so the next thing, if you have any doubt till this, you may ask me. We may discuss, or we may proceed. Okay, anyway, so let us continue. So the next one is the GRU. Now, the thing is, just imagine the number of parameters we need to learn. Can anybody tell me how many parameters do we need to learn here? How many parameters do we need to learn? Anyone? The parameter, but the weight vectors, isn't it? That we are learning through the gradient descent. Okay. So as we know, as we have seen, there are various gating mechanism here along with some additional units. Okay, so definitely we need some kind of parameterization technique for each of the gating mechanism along with the additional units. So definitely just look at here, this is what we have. Then we can have W, that V for the output layer. For we can have this for this part, the candidate one, uh, or this for output also we can have some weighting mechanism, or we can have some parameter. So yes, what this U plus W2. Yes, so 4, yes, exactly 4. Sometimes if we want to parameterize this part also, we may have to learn 5, isn't it? The 4 comes from this this 4 units. If we want to parameterize this one, again this will be overall the number of parameters that we are going to learn is 4, but internally again this dimension will go on increasing. Okay, so anyway, so this is what we are going to minimize with the GRU. We are going to minimize, so we can observe this input, this forget gate is somewhat similar to this gate, that basically the input gate, and this basically this was the output gate, isn't it? So all of them had same input, they have their own weights, so they are basically differing in a sense, we can say the bias and the weights only. So if you will observe these three units, this and this, so these three units basically behaves differently in terms of the weight and bias. Agree? Yes, by LSTM u plus, yes, yes, that is what here he was saying, it is 4. Okay, so now okay, so the thing is we are going to minimize this number of parameters required. Okay, so if you want to minimize it further, what will be the solution? Can anybody suggest me the solution to minimize this parameter, number of parameters required? So this W1 itself, if we talk about this W1, this W1 itself is a vector. Okay, so we need to learn this one, again this one, again this one. So we are going to minimize this part. So can anybody suggest how we can minimize this one? Okay, no answer. Yes, exactly. We are going to combine something so that whatever modules are being basically the modules that are being redundant or seems to be redundant can be basically minimized. Okay, so in GRU that is the same thing we are going to do. What was the first thing that we are going to do in this case? It basically combines merges the real estate, city, and the hidden estate. Okay, so now how we are going to minimize that one? Okay, so let me draw this one. Okay, uh, it will be something like input xt as previously we have seen. Okay, we are going to talk about, okay, and then So this is one thing that this is minimized. So the input is fed xt and st minus 1. This is one thing is 1. Okay. So now the thing is basically earlier where there was a ct and ht. Now both of them has been merged in a single hidden state only. Okay. Now the changes, the slight changes that we can uh, realize is this is somewhat similar to that one that we have seen earlier. If you can recall from there, one product and one summation was there. Okay, so the same thing is there. One product and one summation is there, but the thing has slightly changed. Things have slightly changed. That now this particular input itself, the hidden state itself, will act as ct minus 1 as well as the long term memory. So the same thing is now working as the long term memory as well as the input from the previous state. So the short term memory, there was two input, the long term memory and the short term memory. So now it is having the same thing but in merged way. So we have concatenated, we have added the cell state and hidden state information. Now one will go directly across the RNN units, and the output from this part means the information will be basically shared across the RNN units in a way it was shared through that another input hidden state. Okay, so now if I ask you what this how you can formalize this in an equation. So what will be the formalization of this one? If I want to formalize this in an equation, so now we have a few things here. So the first one is here we have, this is what we say the reset gate, the new terminology that came into, and this one we say update gate, and then this part is basically okay. So what it is doing, whatever information we are having, okay, based on that information we have applied the sigmoid function, and then we have basically selected the same analogy. If you apply, it is going to just select the information that we just want to preserve for the next stage. Okay, so here if we talk about the update gate, let me just, the first thing is okay, what it does, it controls the part of hidden state that preserved. Okay, so if I say uh, if I say that this is value z, okay, the value that is coming is z. Okay, so now if I ask you in mathematically what this equation will look like, will be something. So just look at here. So if we are saying that this is z, so again this can also be written as z, zt, isn't it? You may write it for reset, and for this what we can say, this is the update, so you can write it update. But anyway, this we say that some output is there, and that output is going to be multiplied, and this we say that this is the output gate. So output gate is nothing but, just look at here, what is the input here? This ht minus 1. What is another input? This xt. Okay, xt going through that activation function will produce that zt. Okay, so this is what I have written here. So if you parameterize this one, you can parameterize this whole as wz. Okay, and accordingly you can distribute the uh, weight vector on each of the input output side. Okay, here you can assign one weight, here you can assign one weight, and here also you can assign weight. Okay, so this z1 uh, now, so update gate is nothing but this value. Okay, the update gate will give us this value. Okay, and this value is going to be contributed to the that hidden state information. Earlier it in case of LSTM, it was the potential value, or we can say the amount of information that is going to be contributed in the long term memory. Okay, the second one is the reset gate. So it was previously what we called it, if you can remember the architecture, what it was called earlier. So if you will look at here, so just look at here, we are talking about the reset gate. So how this reset gate is contributing? So just look at here, we have taken this uh, the output of this reset gate. Okay, and then that output is nothing but input to the tanh function, and to the tanh function, whatever it is computing, the intermediate value is going to be multiplied with what value the that update gate has computed. Okay, so if we write it mathematically, what it will be? Okay, So this is the sigmoid function, okay, and this could be the weight matrix, and this is the whole thing. Okay. Similarly, what about the new hidden state? That is, what is new hidden state here? This value, okay, the transient value here. This is, we can say, the h tilde, okay. So basically, if you can recall, so this reset gate uses this information so that how much from this information will be get added to the overall information. This is what it is going to do, isn't it? So this is the transient one. We have applied the 10 tan h, okay, and within that we have some weight vector, okay. Then that reset and the hidden input comma the input, okay. So this is your new hidden state. Now finally, if I ask you what will be this ht, can anybody suggest me what this ht will, what will be the expression of this ht now? So this ht is nothing but, we can say, the output of this part, okay, the multiplication part plus whatever value we have obtained from this final this multiplication part. Both of them will get added, okay. So anyone who can suggest me how we can write this ht? And one more thing, this, what this value is saying, that means the just complementing, means whatever information we are following this side, the remaining will be followed this side, means it is something like a balancing factor, okay. So we can say this is, if this information is zt, so 1 minus zt of this ht minus 1 will come here, isn't it? This is the information that will come here, and plus this part, okay. So this part is, so here it will come, if it is 1 minus jt has gone there, so it will be jt. So the whole information content should be equal to, means it is a fraction. So we, if you remember, this gives us the percentage, okay. So if 50% has gone this side, so remaining 50% will go other side. This is what is happening. So this 1 minus jt plus jt is 100% information, okay. So what, how proportion of information you are regulating through different route, that is kind of balancing factor here. And into this, what is here, this is the h tilde, okay. Okay, so basically, if you will look at this example, definitely in this one, the number of parameters that we learn is, for this gate only we need two gates, the reset gate and the update gate. We have only two gates, the reset gate and the update gate. So the parameter is now reduced. Earlier it was how many gates? How many gates were earlier? Earlier it was 4, now it is reduced to 3, isn't it? We don't need 3 gates here. So if the number of gate itself has reduced, definitely the parameter will get reduced. Okay, and the small change that we have seen is just merging of input and forget. If you can recall from this one, the input, the forget and the input, they have been merged in this one. Okay, the output gate is somewhat similar to what we are still having in GRU. Okay, the cell state and the hinge state now merged in a single part. Okay, so this is the basic of what GRU is. Means when we want, if we want a speed plus less number of parameters, we can go with the GRU, but most of the time we see the LSTM is the most preferred one we are using now, even nowadays. Okay, but thing is, even the LSTM or GRU is still having some kind of problem. Can you tell me whether there is some problem is still there or not? Do we have problem or are we fine with this these architectures, the gated architectures? So basically, if you will look at, so still there are some problem, there may be some gradient problem here also. So for that, the attention you will learn in the next lecture series. So attention and transformer is introduced, and nowadays this one is the most popular. Transformer is the most popular one that we are going to learn. So basically it avoids all kind of gating mechanism. Okay, so anyway, so this was all. If you have learned the LSTM, GRU is nothing but just the combining and merging of the gates. Okay, so let's just briefly have the one code example. Awesome. Yes, if your sequence is very larger, okay, in case your sequence is very larger, so in which one do you prefer, the LSTM or the GRU? So definitely the GRU will be better because of the less number of parameters, but if the sequence length itself is very larger, definitely the gradient problem will still be prevalent in this scenario. Okay, we cannot completely get rid of that one. So that's why we move move on to the next the most updated models like the attention and transformer models. Okay, so just have a look at this simple example. So suppose we are I have taken one example that one sentence is there. Okay, a paragraph is there, and in that paragraph it is basically the line feed is there, means new lines are there. Okay, now we need to map it onto the some words. So either you can go by a character level or the word level. Both way you can basically uh, model the architecture. Okay, so if we go by character level, So what we will do, we should first need to figure out what are the different unique characters in this whole paragraph. Okay. Now, as you remember, in LSTM we had a time sequence ordering. If you recall, the time sequence ordering was there. So we need to process them all, isn't it? So for that, we need some kind of indexing mechanism. Okay. So some indexing mechanism must be there. So the first thing is, we are going to, if it is a character level, so it one set will be formed, and that set will have a set of unique characters in the whole paragraph or the sentence or the sequence that you are providing. Okay. So are you following this code? Is it visible to all of you? Hello? I think the code is visible. Anyone, please? Am I audible?
Yes, sir.
Okay, okay, thank you so much. Okay, so my voice is breaking, I think. Anyway, so I hope it is fine now. So the next thing is, we need to basically sort the values. Okay, so it is something like it will be something like suppose the machine is there, so we are going to map it as okay. So we will have some set, okay, set of unique words, okay, and then the next thing is, uh, we are assigning, we are basically sorting them out. Okay. Sort, the purpose of sorting them out is to basically be easily able to map the values that we are computing against each of the character or the word. Okay. So otherwise what will happen, if we are at character level, this m here will have might have different value uh, compared to this m. Okay. So that's why some indexing must be there to map the m to that particular index and vice versa. Okay. So from that character set, we are basically getting the data size. The data size is basically the whole code, means whole paragraph, the number of characters appearing in that paragraph, if it is at character level. If it is at a word level, so it will be the unique words that are there in the paragraph. Sorry, that the words that are there in the paragraph will be the data size, and the word size will be the unique words that are there in the paragraph. Okay. Now this indexing is to ensure the basically encoding and decoding of the data, so that we can uniquely remap the data or reconstruct the values. Okay. If we do not provide this indexing, definitely we will be unable to reproduce the result or reproduce the values, okay, corresponding to the same character or word. Okay. Now this is the data we are having. Suppose this is the training data we are having. Actually in a real world example, it happens to be a whole corpus of data. It may be the whole Wikipedia page or some corpus of data that you are having. The whole corpus will be used as a training. Okay. So here it is a training and that label. Okay. In the training set, what we need two things. Okay. One is the training sample X and the label Y. Now the question is, what do you mean by label here? What will be the label here? Anyone? What will be the label class label here? Can anybody answer? Anybody? Huh? No answer? Okay. So basically here, since we are providing a sequence of characters, isn't it? We are providing sequence of characters. So it is nothing but the train X will be from beginning to end, while the train Y will be starting from A, not M. Okay. So first we are feeding M. So it is something like this. So the X will be starting from machine and everything will be there, and it will be a starting from and everything will be there. Now in recurrent network, what will happen? If we provide M, it should predict the next word as A, isn't it? If it is not predicting this A, definitely we in the using the B back propagation through time, we will update this weight. Okay. Next time we are feeding A, it should predict C. So this way it will basically what we say, propagate or unroll itself over the sequence of inputs. Okay. So this is the trend corpus words. Corpus word is, but the thing is what that uh, the testing set will contain. That was the question. So I have told you this testing will have just one word. Means it will begin from the next word from where the training set has started. So the training started from M, so testing will start from A onward. Okay. Then since the input cannot directly feed characters, so we need some encoding mechanism because neural network understands only numerical values. So we need some encoding mechanism. Either you can go with the one-hot encoding, or as we have talked earlier, we can go with some embedding technique. Okay. So if we are going with the embedding technique, we can also go with the that word embedding or character embedding, so something like that. Okay. So the purpose of embedding is nothing but to basically suppose uh, in the set, in this set, what is this set? The set was nothing but the set of all the unique characters in the paragraph. Now, wherever that some particular characters have appeared, based on that, that encoding, the one-hot encoding will work. Like suppose in this one, suppose A has appeared at 1, M has appeared at 0. So the one-hot encoding for M will be something like if it is having k number of suppose I'm considering all the alphabet, the whole alphabet as the unique character, all the alphabets are present, so it will have 26 characters. So suppose M is at first place, so this will become 1, and all the 25 places will contain the value 0. Okay. Likewise, for A it will be 0 here, and then for others at the first place it will be 1, and then again 0 0 0 0, something like that. So this is the one-hot encoding. To basically map the characters. Okay. So these encodings will be fed as an input to your model. Okay. Now we need to initialize the weight vectors. Okay. So this is the definition, the function that we use. Okay. So this is a Javier equation. We call it Javier equation to initialize the weight so that the vanishing gradient problem can be minimized. Okay. And either you can define your own sigmoid, how you are going to basically compute the derivative. So you can take it in this way, because this is the derivative values. Okay, not the sigmoid value. This is the derivative value. So as we all know, all of the gates uses sigmoid and 10H. So my question is, can we use some other activation functions here rather than sigmoid or something, the 10? Can we use? So what will happen? Yes, exactly, very true. But what will happen then? So if suppose we are not providing any activation function like sigmoid or tan, so definitely the default one is sigmoid, and if you are not specifying anything, definitely it will be like a kind of linear activation function. So whatever input is coming will go to the next level, and that way it will basically overload the information. So the kind of vanishing gradient or exploding gradient will be, the chances of happening those problems will be very higher. So that's why we use the sigmoid and tanh function to squeeze the information, okay, to squeeze the information in some smaller range. Okay, so this is the function that you can apply. The softmax, you know, for multi-class classification, we can go with the softmax function. Then we have different weights we need to initialize. Okay, so as I have told you from this diagram, if you recall, so we have different weights W1. So input gate, forget gate, input gate, output gate, then candidate gate, gate out this some what we say, this is the potential, we can say, the output, we can say. So these things we need, the weights for these gates and units we need to initialize. So this is what we are having. So for forget gate we have weight, for bias weight, for input gate bias, for input gate weight, for candidate uh, information, bias for that candidate information. This is for output that I have written in terms of V. Okay, and this is sorry, this is the one that I have written here, and this is the one that we are talking about here. Okay, I think you are following this one. Okay, then this is the reset mechanism. So now the thing is, okay, suppose I have trained a model on this corpus. So this model will only be able to predict in this context. Whatever input you will provide, based on that input, it will only predict in this context only. But suppose if you want some the model in some other context, if you provide some sequence from other domain, definitely we need to first reset that one. Okay, all the parameter values will be set to 0. But suppose we are having a large corpus and we don't want to reset the values, because as we all know, in order to learn the context, the weight matrices must be shared across the time unit. So even though for larger corpus we divide it into tokens or statements, okay, or sentences, there we will not use this reset one. Okay, this reset one is only used in case of where each time we are providing a different sequence in different context. Okay, if we are working in the same context providing again and again different sequence, so we may avoid this one. Okay, now this is the forward pass. Okay, in the training. Okay, so in the forward pass, just look at here, we have the forget gate, input gate, candidate gate, output gate, and cell state. And this is basically how we have seen this one. So the forget gate, if you will look at here in this example, so what was the forget gate? It was the multiplication of these two values. So the forget gate weight matrix plus input, okay, and the self sorry, the bias of the forget gate. Okay, it will be combined with the other values along with that one. So this is the naive implementation. Okay, so likewise you can manipulate upon these functions. Okay, So we are computing the cell state, the hidden state, according to this equation only, according to this provision only, whatever we have basically learned here. This is the provision that we are basically implementing here. Okay. This is just to print the intermediate values of the gates. Okay. And then once we complete the forward pass for the whole sequence length, we need to back propagate. Okay. So this is the back propagate through time. So this is how the gradient will work. Okay. So the gradient function will compute for each of the loss. So whatever loss function we are incurring, okay, each time we are computing the loss value, and the gradient will flow in this direction by computing the losses from the last unit. Okay, and that will get on propagating to the previous layers, previous RNN units. This is one unit we have. Based on, if we have thousands of characters, so definitely we need, if we have, suppose if we have 1000 character, how many RNN unit do we need? RNN units. So in abstract term, we can say that that many time units we need, and that many RNN unit will be there. Okay. Okay. So this is the gradient computation. We have used tanh for the candidate, and for other it is the sigmoid only candidate, and for the output we have used this tanh, and for others we have used this sigmoid. Okay, and this is to just debug the values while running. Okay, so now this is the definition for training the value. Okay, so we are also computing the, applying the softmax function to predict the values. Means suppose uh, uh, anyway, so I think I had written somewhere. Okay, I wrote somewhere. Anyway, so basically the example was something like what I was saying. So suppose these were hidden units. So what it is going to predict? Okay, here we are going to apply the softmax. Okay, so this probability, this will help us to compute the gradient back. Okay, and based on that softmax, we will predict which character will appear, and once the character is decided, we will basically compute the error. Okay, so this is for debugging purpose. So let me just compile this one. So here what I am doing is, I have taken the hidden size of 25, means in each of the unit, in each of the RNN unit, what we are going to do is, we are having 25 numbers of that neurons, we can say. Okay, and then whatever encoded vector size is the one auto encoded size, so we are going to basically combine it as the input size. Okay, the hidden size plus the character, the unique character size. Okay, so and the train x is nothing but your the corpus, and the train y is nothing but the leaving the first character. And then you can test it on some different data also. I have tested on the same data, but you can basically test it on some different data, and you can just look around how it appears, and just look at here, the soft, based on the softmax values, the characters are predicted and the error value will be computed. Okay, and accordingly it will back propagate. So if you look around, just look at here how much accuracy we have obtained. So if you will run it again and again, it might vary. Okay, so anyway, this is just one toy example, we can say. You can take any corpus if you are working in kind of NLP or any one of the problem that we have seen here. Okay, so you can basically have any of the application of this LSTM. Okay, so in any of the application you can go with this, you can extend this example to any of the application. Okay, so okay, one more question. If I ask you what kind of architecture I was implementing through that implementation, which of the architecture it is? Is it a vanilla NN? Is it a image captioning? Is it a sentiment classification? Is it a machine translation or frame level video classification? What architecture we are implementing here? Can you tell me? Can you tell me what architecture we are implementing here? The training part, where it is? Yes. Huh? Just by looking here, can you tell me what kind of architecture we are having here? Or in simpler term, if I ask you what kind of architecture is it? One to one, one to many, many to many, many to one? What kind of architecture is this? Yes, yes, very good. So basically it is a kind of many to many, but we can basically extend it to any of the example that we have basically uh, just seen here. Okay, accordingly the architecture need to be changed, but you can extend it to that one. Okay, any question on this one? So I think we are done for the session. So any question if you are having, just let me know. Yes, it was machine translation actually. Yes, yes. Any question? So basically for this one, where it will be overruled, I think nowadays uh, wherever we are talking in terms of NLP or what we say, the sequence to sequence or sequence modeling, nowadays transformer architecture is overtaking those things. Uh, the the benefit of using transformer is basically the number of parameters, and the way we have used the gating mechanism in LSTM as well as in this what we say the GRU is uh, basically this architecture avoid those things. Okay, so I'm not sure for that. Definitely we will have to look for the research papers where it is claimed to have the overruled the transformer, but definitely a recent publication says that out of 100 papers if you look for, definitely around 60 to 70 paper will be based on the means in recent articles 50 to 60 will be based on transformer attention and transformer, while very less number of them will be based on the RNN. Okay, so it is just one advanced form of this LSTM where the gating mechanism is again is basically absent. Okay, so I'm not sure that what actually in which application it will overrule the transformer, but definitely it is a nice question. I will definitely explore this one. Okay, thank you, Krishna. And anyone, any more question? Okay, thank you all. Thank you so much for actively participating in the session. So the next session will be starting, and that will very much interesting even for me. So the next session will be taken by Dr. Mahipal Jadeja sir. He is actually his research area itself is in this graph neural network, and definitely I will also attend the session, and I hope you all will enjoy the session. He is having very good experience in delivering talks on these topics, so hope you will enjoy.